Greetings from the Department of ECE. We'll be discussing about the part B, which is under Module 3, Embedded Systems. In that, ARM Processor Fundamentals, which we'll be discussing about ARM Core Data Flow Model, General Purpose Registers, and CPSR, Pipelining Concepts, Exception, Interrupts, and Vector Table, followed by the core extensions. So as you can see the diagram of ARM core data flow model, ARM you can means you have a set of registers, general purpose registers like R0 to R15. Then you have a sign extension. We'll discuss about each and everything. Why do we have? And you have a data bus, address bus, and you have an address register with an incrementer, auto incrementer, to point to the next memory location. That means PC program counter, which is a register 15, which holds the address of next instruction to be executed. Suppose if it is starting with the first instruction, next instruction address with an auto increment operation, PC will be incremented. Then you'll have a ALU, arithmetic and logic unit, inline barrel shifter. Suppose if you need a shift operation, that you can perform through inline barrel shifter, and otherwise you can go with a normal arithmetic and logic operations. You have along with that MAC, multiply and accumulate unit. After multiplying the here accumulator is the one register which is used to store the intermediate result, and again it can be stored back to the register file, so that we are denoting here as RD. Suppose if you are fetching the data, means whenever you write a program, that program has to be stored into the memory. So from memory you will be fetching the instruction, then executing the instruction, decoding it, and then executing. So in order to fetch the data from the memory, we will be using the program counter PC, which holds the address of the first instruction, next instruction to be executed. First it gets the first instruction and it will be auto incremented. The instruction whatever it has fetched, which will be sent to the decoder, instruction decoder. So that decoder will decode the instruction, and machine can understand the which operation to be performed, if it is a ALU or MAC operation, which will be performed through the registers. In order to perform ALU operation, you need one or two operands. So those operands can be stored either in registers. That content you can fetch from the memory, sent to the registers. After performing the arithmetic or logical operation, the result has to be stored again back to the registers. So result which is in RD will be stored back. That's what the major diagram illustrates about. So as you can see, ARM core, which is as a functional unit, which is connected by the data buses, as you can observe. So it is a von Neumann implementation of the ARM architecture. That means the data items and the instructions which will share the same bus. If it is a hardware implementation of ARM, then it uses two different buses, one for carrying the address, another one for carrying the data. As it is a von Neumann architecture, uses the same for carrying the data as well as the instructions on the same bus. An instruction decoder, it decodes or translates the instruction before it gets executed. Each instruction executed, it belongs to a particular instruction set. We'll see that instruction set in the next module. So ARM processor, which is a RISC processor, uses a load store architecture, meaning there are majorly two types of instructions for transferring the data in and out of the processor. One is load and another one is store. Store means copying the data from register to memory. Load means copying the data from memory to the registers. There are no data processing instructions that manipulate the data in the memory directly, so which has to be carried out in the register. The data items which are placed in the register file, which is a bank of 32-bit registers. Since ARM core uses a 32-bit register, 32-bit processor, it uses a 32-bit registers. Signed extension converts that signed 8-bit or 16-bit data to a 32-bit value as you are reading the data from the memory and is placed in a register. ARM instructions have two source registers, RN and RM, and a single destination register. Usually we call it as RD. The source operands are read from the register file using an internal buses, which we call it as A and B. You have either ALU or MAC, multiply and accumulate unit, which takes the register values and computes the result. So the data processing instructions writes the result RD in RD directly to the register file. So load store instructions uses the ALU to generate an address to be held in the address register and broadcast on the address bus. So an important feature of ARM is that register RM alternatively can be processed through a inline barrel shifter before it enters into ALU. Together with barrel shifter and ALU, you can perform wide range of expressions and addresses. After passing through the functional units, the result in RD is written back to the register file through a result bus. So you will have a auto incrementer to update the address register before the core reads or writes the next register value from or to the next sequential memory location. So the processor continues execution until an exception or an interrupt changes the normal flow of execution. This is about the ARM core data flow model. Next topic which we will discuss is about the register set which is available in ARM processor. So coming to these registers, so you have a general purpose registers of 16 general purpose registers, R0 to R15. So it can be used to either hold a data or address. You can observe the active registers which are used in the user mode. We'll discuss about the modes soon. The processor can operate in majorly 7 different modes. There are up to 18 active 32-bit registers. So 18, under that 18, 16 are data registers and 2 are processor status registers. In that you have CPSR and SPSR. Coming to 15, the data registers, they are from R0 to R15. So majorly among all these 16 general purpose registers, 3 are meant for performing a special operation. They are R13, R14, R15. R13 we call it as a stack pointer, which is used to hold the address of the top of the stack in the current processor mode. Whereas next one R14, which is a link register, it is used to store the return address whenever you call a subroutine. During the subroutine period, we'll make use the link register to store the return address. Next one is PCR15, program counter. It holds the address of the next instruction to be fetched by the programmer. In ARM state, you have R0 to R13 registers which are orthogonal. There are two program status registers, as I said, CPSR, current program status register, and saved program status register. So coming to the next topic, which is about the CPSR. We have seen about now core data flow model and the registers which are available in ARM processor. Orthogonal indicating any instruction that you can apply to R0 can equally be applied to any other registers. Most of the times we will be using registers from R0 to R12. R13, R14, R15 are meant for special purpose operation. Most of the times we won't touch that. Next one, which is about the current program status register, CPSR. So ARM uses CPSR to monitor and control the internal operation. All the registers are of 32-bit size. Even CPSR is also a 32-bit register, which is used to control and monitor the internal operation. So if you look into the diagram, you have majorly 4 fields in the CPSR. You have a flag field, status field, extension field, and control field. So each and every field is of size 8 bits, 0 to 7. So first field, if you observe, control field 0 to 7, again here it has been divided into different bits meant for different purpose. The first 5 bits, that is from bit number 0 to bit number 4, is meant for selecting the processor mode. There are 7 different processor modes. So in which mode you are supposed to work can be decided based on the board operation, specific mode. So here you can observe, if it is a user mode, you need to write a binary data to CPSR register as 10000, last 5 bits, the first 5 bits, 0 to 4, bit number 0 to bit number 4. If it is a system mode, then you need to write the data as 111 5 ones. FIQ indicating fast interrupt request, IRQ indicating interrupt request, SVC indicating supervisory mode, next abort mode and undefined mode. So there are 7 different modes which you can select by sending a different code to the CPSR register to the first 5 bits, that is from bit number 0 to bit number 4. Next 3 bits are IFT. T in bit number 5 is a T bit indicating thumb state or ARM state. As already discussed, ARM supports both 32-bit instruction set and 16-bit instruction set, which we call it as a thumb state. So suppose if I want to enable thumb state, or if I want to shift to thumb mode, the T bit in CPSR register must be high. If it is ARM mode, by default that should be made as 0. Next you have is 2 interrupt requests. One is fast interrupt request and interrupt request. Masking of that, which you can do by I and F, corresponding I and F bits as high. Suppose if I bit is made as high, indicating interrupt request has been masked. So that means that means the processor core won't accept any interrupts when I bit is set to 1. Next, extension and status fields are meant for future purpose. Next, flag fields that we have, which is N, Z, C, V, Q, different conditional flags based on arithmetic or logical operations, data processing operations. The corresponding flag bits will be enabled, indicating negative. Suppose if I get a negative result after performing a LU operation, then n bit is set to 1. If the result is 0, then Z flag is set to 1. If you are having any carry after performing a LU operation, then C bit is set to 1. If you are having any overflow of data, then V bit is set to 1. If it is a saturated ALU saturated operation, then Q flag bit is set to 1. So along with this, you have a J bit meant for Java bytecode execution. It also supports that J bit. So that's what the same thing which is given over here. You have 4 fields, each of 8 bits wide. Flag bits, status bits, extension field and control field. And a control field, you have a processor mode, state and interrupt mask bit. Flag fields, you have a conditional flags. So you have, apart from this, J bit, which is meant for performing JAGL enabled processor Java core to execute. So this is about CPSR register. So in CPSR register, as I told, you have 7 different modes. So the processor mode, it determines about which registers are active, and the access right to CPSR register, whether you have or not, is decided based on which mode you are in. All the processor modes are divided into 2 types. Either it could be privileged mode or non-privileged mode, indicating whether you have a full read-write access to the CPSR or not. So in case of privileged mode, you will have a full access, read-write access to the CPSR register. In case of non-privileged mode, it allows only read access to the CPSR fields. But still it allows read-write access to the conditional flag bits. There are 7 modes, as I told you. You have a 6 privileged mode and 1 non-privileged mode. So coming to the 6 privileged modes, you have indicating a full read-write access to the CPSR register. So abort mode, fast interrupt request or interrupt request mode, supervisory mode, system mode and undefined mode. Abort mode is when a system is failed to when the system you have a failed attempt to access to the memory, then it will enter into abort mode. Fast interrupt request or interrupt request mode, which corresponds to the interrupt levels. Whenever a peripheral device needs a request of accessing the core, then either FIQ or IRQ mode, it will switch over. Supervisory mode indicating after the reset, generally any mode that that it has to run the operating system kernel. So system mode, which is a special version of user mode. So as it is a privileged mode, you will have a full read-write access to the CPSR. Whereas user mode is a non-privileged mode, you will have a read-write access only for the conditional flags, not for the mode changing. Undefined mode, when the processor encounters an instruction that is undefined or not supported by the implementation. So during such cases, it will enter into undefined mode. User mode, which is the one used for writing the programs and applications. So the figure shows you have in all the modes about 37 registers. So in the user or system mode, you have access to R0 to R15, 16 registers and CPSR. So 17. In fast interrupt request mode, apart from means you have R8 to R14 FIQ register. Along with that, you don't have a CPSR access, then SPSR will be there. As it is moving to interrupt request mode, the processor register has to be saved. to SPSR. So even in interrupt request, R13, R14, R13, R14 are stack pointer and link register. So in each and every mode you will have a separate stack pointer and link register along with that SPSR. Whereas only in FIQ mode, apart from SP and LR, you have R8 to R12, total 5 additional registers. So together constituting about 20 registers which are hidden from the program at different times. So these registers, which we call it as a banked registers, and are identified here by shading them in the diagram. So the banked registers are available only when the processor is in a particular mode. Suppose if it is in abort mode, we will be writing like R13 underscore abort. So that underscore will be specifying the mode. So the processor mode except the user mode can change the mode by writing directly to the mode bits of CPSR. Suppose if it is in FIQ mode, from FIQ mode you can shift to any other mode. As it is a privileged mode, you can write the data into CPSR mode bits. All the processor modes except system mode have a set of associated banked registers. There are a subset of main 16 registers. The banked registers maps 1 to 1 onto a user mode register. If you change the processor mode, banked register from the new mode, it will replace with an existing register. Whenever you have an exception or an interrupts, so it can change the mode, reset to interrupt request, fast interrupt request, to any of these modes. So the following figure which illustrates that. Suppose the core has changed from user mode to interrupt request mode. So then what happens is, whenever an interrupt is raised due to an external device raising the interrupt to the processor, R13 and R14 are banked registers. The user registers are replaced with registers as R13 underscore IRQ, R14 underscore IRQ. Usually R13 holds the R14 holds the return address, R13 holds the stack pointer in interrupt request mode. Coming to CPSR, CPSR will be saved to SPSR. To return back to the user mode, a special instruction which will be used in the during the interrupt and instructs that core to restore the original CPSR from SPSR and bank in the user register, that is R13 and R14. SPSR will be modified and read only in privileged mode. There is no SPSR available in user mode, that you can notice even in the diagram. It's another important feature of CPSR is it is not copied into SPSR. When the mode is changed, forced due to program writing directly to the CPSR. So various modes and its associated bit patterns that you can observe in this diagram. So for the abort mode, you will have whether it is a privileged or non-privileged, you can observe, and the mode bit pattern that you can observe here. The same diagram which you can observe accessible of the registers in user mode, FIQ mode and IRQ mode are in different modes. So as the T bit, as I told, which is used to determine whether it is a thumb instruction set or ARM instruction set which you are using. Suppose if T bit is 0 in case of CBSR register, it is default 32-bit ARM instruction set which you are using. If T bit is 1, indicating 16-bit instruction set which you are supposed to make use. So you'll have a Jazzle core, J bit if it is set to 1, Java core to execute, Java bytecodes to execute. So this is the diagram which indicates the differences between ARM and thumb instruction set. If you observe, instruction size in ARM case it is 32-bit, in thumb case it is 16-bit. Coming to core instructions, you have about 58 core instructions in case of ARM processor. You have 30 core instructions in case of thumb. Almost all are conditional execution. Instructions are of conditional execution in case of ARM. Only branch instructions are conditional execution in case of thumb. Coming to data processing instructions, it allows access to the barrel shifter and ALU, whereas in thumb you have a separate barrel shifter and ALU instructions. They are different. That we'll discuss during the module 4. Coming to PSR, it is a read write in privileged mode, whereas in thumb instruction set you don't have a direct access to PSR, CPSR register. Coming to register usage, you have 15 general purpose registers including PC, whereas here low and high registers, that you have 8 general purpose and 7 high registers including PC program counter. So this is about the Java codes, as we have discussed about already these things. So next class we will discuss about the interrupt masks, interrupts, exceptions, conditional flags, then followed by conditional execution, pipelining, pipeline execution, ARM core extensions, vector table core extensions. Thank you.